Today we're going to explore Drizzle, what it is, how it works, and why it matters for astronomical imaging. Drizzling was developed in the late 1990s for the Hubble Space Telescope. The telescope faced a classic problem. The Hubble's cameras didn't fully match the telescope's optical resolution. The detectors were undersampled, meaning each pixel covered too much sky and fine detail was lost. To recover that hidden detail, they devised Drizzle, a way to combine multiple dithered exposures, redistributing each pixel's flux onto a finer grid. This allowed the Hubble to achieve sharper images without changing the hardware, and we're able to use this process too. Drizzle can be a bit of a head scratcher at first. If you felt that too, you're in good company. Let's take a closer look. Supersampling can be thought of as sampling the same scene at a finer resolution than the detector natively allows. Drizzle is a supersampling technique. It recovers subpixel information that standard stacking suppresses. Think of it as redistributing each pixel's flux onto a finer grid. The key requirements, though: frames must be dithered and registered, and it works best with many well-dithered subframes, especially in undersampled systems. It is worth noting that some amateurs report that drizzling works well even with well-sampled data. A pixel records the total flux, that is the number of photons that reached it during the exposure. But that measurement isn't perfect. It depends on the detector's quantum efficiency, which is the probability that an incoming photon is actually converted into an electron. It's also affected by noise sources: read noise from electronics, dark current from thermal electrons, and shot noise from the random arrival of photons. So, when we talk about a pixel's flux value, it's really a combination of true signal plus these detector characteristics. After registration, each pixel can be mapped to a specific patch of the sky. With dithering, that patch is sampled multiple times at slightly different detector positions, giving us overlapping measurements of the same sky region. The drizzle grid is at the heart of the drizzle idea. It's a scaled-up matrix persistent through the process. It accumulates flux and weight simultaneously, serving as both the working ledger and the final image container. You could think of the drizzle grid as a finer mesh where all contributions are recorded. A drop is a shrunken pixel footprint scaled by the PixFrac parameter. This parameter is called drop shrink in PixInsight. Flux is conserved. Smaller footprint means higher intensity. Each drop is mapped onto the drizzle grid, redistributing flux according to overlap. We'll be looking at this drop diagram in detail in a few minutes. Looking at the drizzle grid operation in total, first we map the pixel center to the drizzle grid, then construct the drop footprint, find any overlaps, and compute fractional coverage as we do so, and then redistribute flux. Each additional frame will have a fractional pixel shift of position. This fractional shift is key to the success of Drizzle. Without it, we would just get image upscaling. If a Drizzle grid already has contributions, then the flux is accumulated, not replaced. And the final step is normalize the flux by weight to get the true brightness. Over the next few slides, we will look at how the input pixels map to the Drizzle grid. Here we have the simple case of a single input frame mapping onto the Drizzle grid and with a dither offset of 0. Let's say the original frame has a single pixel with a flux value of 1. This means that each cell in the Drizzle grid will receive 0.25 units of flux for each of its corresponding 4 cells. This is a scale 2 Drizzle, giving us a 2 by 2 finer grid. The dither offset of 0 means the transferred pixel lands in exactly the same place as the detector, no subpixel shift. In this case, Drizzle behaves almost like a simple upscaling. The flux is redistributed across the finer grid, but exactly centered. The flux split evenly into 4 cells. Flux is conserved, but the result is just a scaled version of the original pixel. Dither data creates the subpixel offsets from frame to frame that we're looking for. Without fractional dither offsets, Drizzle doesn't add detail, it only interpolates. It's also instructive to look at what the addition of a null frame, say a frame with all 0 flux values, would mean. In this case, there is no change to the Drizzle grid. No new flux values are added, and importantly, no new weights for the Drizzle grid cells either. In a moment, we'll look at what happens when we add a dither. That's when Drizzle starts to recover hidden subpixel information. Here we've added a second frame with a fractional dither offset, 0.5 pixels in X and 0.5 in Y. And for those that prefer grayscale image, in their original paper, the authors illustrated Drizzle with apparent rotations, but that's just a diagrammatic effect. No actual rotation is applied by the technique other than the field rotation that might exist between the input frames. The point is, dithers fill gaps and create supersampling by redistributing flux according to the overlap percentage. Each pixel in the input frame is mapped to the Drizzle grid using its registered sky coordinate. This mapping often lands at a fractional position on the grid, not neatly on the cell center. From that fractional position, marked here by the yellow X, we construct a drop, a smaller footprint that carries the pixel's total flux. The size of the drop is controlled by the pixfrac parameter. Pixfrac of 1 means the drop is the same size as the original pixel. Smaller values shrink the footprint. Even though the drop may appear to cover more grid cells, it actually represents a smaller angular area on the sky. That's the key. Drizzle shrinks the drop footprint, not the flux. We then calculate how much of the drop overlaps each surrounding Drizzle grid cell. This is a geometric operation. We're slicing the drop into fractional contributions. The pixel's flux is redistributed across those cells according to the overlap percentage. If a cell receives 20% of the drop's area, it gets 20% of the flux. This redistribution is flux conserving. The total flux from the pixel is preserved, just spread out more finely. As more frames are added, these drops accumulate on the grid, building up a sharper, higher resolution image. We can think of each pixel as a Gaussian bump, signal plus noise. Drizzle smears that bump across several finer cells. The signal is redistributed, but so is the noise. That's why Drizzle reduces per pixel noise, but increases correlation between neighboring pixels. In other words, Drizzle doesn't eliminate noise, it splatters it across the finer grid. Before Drizzle, pixel noise is mostly random, uncorrelated from one pixel to the next. That kind of noise is relatively easy to reduce using standard techniques. But Drizzle redistributes each pixel's flux and its noise across multiple output cells. That means neighboring pixels now share noise contributions. The result is correlated noise, structured patterns that mimic real features, making them harder to detect and suppress. So Drizzle doesn't just spread the noise, it changes its nature. It turns random speckles into blotchy textures that overlap with faint structures. Some warning signs to watch for in drizzled images. Checkerboard or grid-like artifacts, and that indicates that PixRack is too small or that you have poor dithering. If you see a blotchy background, that's probably the correlated noise which is dominating the image. And if you get no detail improvement, the data was probably not truly undersampled. At a scale of 1 by 1, Drizzle improves how geometric distortions are correlated and preserves existing PSF structure, but it cannot correct optical aberrations caused by incorrect backfocus, for example. Geometric distortion refers to errors in where the light is placed in the image plane, not how it is distributed within a star's PSF. Scale 2 by 2, that's super resolution, but correlated noise increases and it requires many good dithers. Higher scales, 3 by 3 for example, demand strong evidence of undersampling and lots of frames. So each pixel becomes a drop mapped onto the Drizzle grid. The flux is conserved, the weights are tracked, normalized output recovers the sub-pixel detail. A few thoughts on good drizzle conditions. We need undersampled data, non-integer dithers, many unique frames, and scale 2 is a sweet spot for many amateur setups. To conclude, Drizzle combines multiple dithered exposures to recover hidden subpixel detail, producing higher resolution images. It's powerful only when the prerequisites, dithering, registration, and enough frames are met.